Okay, lesson 2.7 kind of gets tacked on to the end of Unit 2. It does somewhat deal with transformations, but it's a little bit different in the sense that you're not flipping it over the x-axis or the y-axis. You're not just moving it around. You're taking the inverse of a function. What's a really actually interesting connection is that the inverse of a function, by the way, an inverse is anything that undoes something. So if you take x plus 3, the inverse would be to subtract 3. You'd undo what was being done.
Should we do a definition?
So when you take the inverse of a function, you're basically doing the opposite function in a little bit of, that's not really a great way to say it because it's not the opposite, it's the inverse. When you take the inverse of a function, it ends up being a reflection over the line y equals x. So you don't need to draw this, but if you had a function, well, we are going to draw it because I'm going to write the definition of inverse of a function. So let's start there. Inverse of a function. Couple things. Number one, it is denoted. That means this is the symbol that you used for it. It's denoted f to the power of -1. Okay, this is called the inverse function of f. Denoted f. This is the inverse function of f. This is the property that it has. Satisfies this property that if you took f of a, so you take your function f of x and you put in any number a, you will get out some value. Okay? Now, in the inverse function, if you put b in, remember that inverse undoes something. What's going to come out?
Why'd you do the comma? What is that?
Oh, sorry, I did. I'm stuck in calculus mode. That's a different symbol. Good call.
Mistake?
One mistake. Yep. In the inverse function, remember the inverse function is going to undo the original function. So what would happen to b if I put it into the inverse function? What's going to come out? A. It's going to come out.
Science.
Okay. Now we can do this with really simple. So I'll give you an example. Really simple one. Let's take the function f of x equals x plus 3. Okay? What happens if I sub in the value 2? What do I get out? I get x plus 3. 2 plus 3 is 5. Now, the inverse function of f of x is this. F -1 of x. Remember, inverse undoes. So this one was x plus 3. That means I'm going to have to take my value and subtract 3 to undo it. Well, watch what happens when we put 5 into that function. What do we get out? 5 minus 3 is 2. Okay, it's just a really simple linear function example, inverse. Inverse functions, they satisfy the property. If I put something into the original function, I'll get something out. If I take the inverse function and put the output in, I'll get out my original input. That was a mouthful, but that's what's happening. So this -1 symbol has nothing to do with exponents or powers, has nothing to do with, multiplying something by itself or anything like that. It's a special symbol that just means the inverse of f. Okay? It's not an exponent. It's a superscript. Superscript is any script that is above, a subscript goes below. It's a superscript symbol that means the inverse of f. So you know that the inverse of f is going to undo f. Okay, one more thing I want to draw for you then is another example of inverse functions. Okay, so you have a little example over there. That's with function notation. I'm going to do one with a graph.
Is this graph?
No, this is still up in your notes. Okay, so over here, we're going to talk about the stopping distance of a vehicle at a particular speed. So speed is going to be our independent variable. And then we're going to have distance here. So this is the distance it takes for a car to stop. Okay? Now, you're right. The faster the car is going, the longer it's going to take for it to stop. Correct? You're driving 20 kilometers an hour, you slam on your brakes, you stop pretty quick. When you're driving 120 kilometers an hour, you slam on your brakes, it takes a while to stop. That graph, in reality, looks something like this. Okay? Now, what taking the inverse does is it actually swaps your dependent and independent variables. So it says instead of on the horizontal axis having speed and on the vertical having stopping distance, we're going to have stop distance on the horizontal and speed on the vertical. And look at the relationship that happens. By switching the variables, we changed the graph and we actually reflected it over the line y equals x. So the inverse of any function, if you're graphing, is simply a reflection over the line y equals x, which is a reflection over y and over x. So in example 1, we're going to determine the inverse numerically. So example 1, we're determining the inverse numerically. We're given a table, and is your table blank?
Yes.
Okay, so we have points
Thank you.
on the function. And then we have points on the inverse function. That's written for you already?
Yeah.
Okay. What I would then like you to do also is this. We're going to write f of x here and f inverse of x there. Okay, we're going to use up our first boxes to do that. That's okay. Now, I'm just going to give you a bunch of points that are on the grid. Okay, so on the original function, you have negative 5, 0. You have negative 4, 2. You have negative 3, 5. You have negative 2, 6. And you have 0, 7. Now what we need to do to get the inverse, because it is a flip over y equals x, all you need to do is switch the y coordinate and the x coordinate.
Oh, that's simple.
Okay, and in this one it's pretty simple because these are just dots. This isn't a curve or anything like that. They're just dots. Okay, so why don't you take a few seconds first and in one color, maybe pencil or dark or whatever, go ahead and plot all these points on your grid. Okay, go ahead and plot all these points on your graph. Pause it and do that and then come back. So the point of this example is really just to see that reflecting something over y equals x is the same as changing the x and y coordinates within each point. So what we're going to do to get the inverse of f of x is just switch the x and y coordinates. So over here, the coordinates, instead of being negative 5, 0, on the inverse function would go through 0, negative 5. Instead of going through negative 4, 2, the inverse function goes through 2, negative 4. Instead of going through negative 3, 5, the inverse function goes through 5, negative 3. Maybe now you're seeing why it's such a big deal when, you know, back in grade 9 and 10, when you were learning how to graph, it makes such a big difference. Which coordinate is which? X and Y. Yeah. Always the same order. Hopefully we're past that. What? Otherwise you're going to be real tricked up.
Wait, let's compare.
Okay, go ahead and plot those new points. Go ahead and plot those new points on the graph and just check to see whether or not it does look like a perfect reflection over the line y equals x.
Were we supposed to plot those first points? Yeah. Oh,
so you should see that they do reflect each other really, really well over the line y equals x. The second thing that we are asked to do is get the domain and range of both functions. So we're going to do that by using mapping diagrams. Okay, so we've got f of x here, the inverse of f here. Okay? Here we have domain. Here we have range. Here we have domain. Here we have range. So in our original function, what numbers make up the domain? Well, they're the x coordinates, right? The inputs. So we've got -5, -4, -3, -2, and 0. And where do they map to? Well, they map to 0, -4 maps to 2, -3 maps to 5, -2 maps to 6, and 0 maps to 7. So now you have the domain and the range. If you want them to really look like a mapping diagram, then maybe we should just do a little bubble around them. Now let's take a look at the domain of the inverse function. So now we're looking at the x values of the inverse function. They are 0, 2, 5, 6, and 7. 0 maps to -5, 2 maps to -4, 5 maps to -3, 6 maps to -2, and 7 maps to 0. What did you notice?
It's a reflection.
Yeah, the numbers pretty much just switched places, right? The domain of the original is the range of the inverse. And the range of the original is the domain of the inverse, because all of our x's became y's and all of our y's became x's.
That's literally all it is.
That's all it is.
That's so easy.
So what about when we get more complicated functions? How do we determine the inverse function? The function that will undo the original function, okay? Here are 4 steps. If you can fit them at the bottom of 26, that's great. If you need to go to the top corner of 27, that's fine. If you have room at the top of 26, that will work as well. If you don't have any room, you could think about the back or just underneath example 2 there. But here are the steps. Steps for, you don't need a ton of space. Steps for determining a function's inverse. Steps for determining a function's inverse. Number 1, write equation in y equals form. So whatever it looks like, make sure it just has y on one side and the rest of the equation on the other side. Once you've done that, you might not have to do that every time. It might be given in that form, but sometimes you're going to have to add or subtract or use BEDMAS to isolate y on the left side. Next step, swap x and y. You literally, where you see a y, you're going to change it to x, and where you see an x, you're going to change it to y. Once you do that, y will no longer be by itself. So you're going to solve for y again. Solve for y in this new equation. When you do that, you will have created an inverse function, okay? But what you need to do is rename it, because you can't have, it's useless if you have the original function as y equals yada yada yada, and your inverse function is y equals yada yada yada. You don't know which is which or that it's an inverse. So you're going to rename it f inverse function f of x. Okay, this is in the case when you start with steps for determining a function's inverse. It should say the inverse of f of x. Like let's say you're starting with f of x. And to get the inverse function of x, you're just going to swap x and y and then solve for y. Okay, I'm going to leave those steps up there as we go into example 2.
Wouldn't another way?
So example 2, we're going to use this strategy and we're going to determine the inverse of a function algebraically. So for each f of x, the first one that we're getting, a, f of x equals 2x minus 3. Okay, I'm going to follow the steps just like they are above. So step number 1 says replace f of x with y. Y equals 2x minus 3. Now nothing new is there. for all intensive purposes, f of x is just another name for y. We often write this, y equals f of x. It just means the graph of the function is determined by this function. This is this function. That's all that means. So subbing out f of x and y, that's the same. Nothing has happened.
Oh,
So you don't,
Okay?
you don't swap the x's for y's though? You only swap the y's for x's?
Step 2, swap x and y. Change their position. So x is going to go here and y is going to go here. Step 3, solve for y. So now y is not isolated anymore, but I can do things algebraically to this equation in order to isolate y. Okay, that's
You didn't do step 2.
okay. So I'm going to add.
You didn't graph it.
No one ever said I had to graph it. All I have to do.
Graph f of x and its inverse.
Swap
No.
That's not the kind of steps to
I'm doing these steps literally right here that we talked about earlier.
I'm dumb.
Okay, so I'm going to add 3 to both sides. I'm doing this in baby steps. This won't always be the case. So x plus 3 equals 2y. Then I can divide both sides by 2. I end up with y equals, maybe I should just write it this way. I end up with x plus 3 over 2 equals y. And in step 4, I'm going to rearrange it and rename it. I'm going to change this y to an inverse function of x notation. And the function is x plus 3 over 2. This is now the inverse of the original. It will undo everything that the original does. And you can see it clearly. The operations have been reversed, right? It had 2x minus 3. Well, now we have adding 3. This x was being multiplied by 2. Now we have the whole thing being divided by 2. Okay, these are inverse operations. This is how you do it. You follow these steps. Not super tricky. Okay, let's graph it. So the original graph, 2x minus 3. What can you tell me about that graph? What does he look like?
It's gonna be.
It's linear.
It's gonna have a vertical.
It's linear. It's a straight line. It's in y equals mx plus b. So what's the y-intercept? Negative 3. 1, 2, 3. What's the slope?
2.
2. So something like this. From negative 3, you have a slope of 2, positive 2. Up 2 over 1, up 2 over 1. Rise over run. Okay, looks something like that. Now, how do you think we're going to determine the inverse function, the graph of the inverse function?
Well, you see, it's probably just 3 and negative 2.
The graph of the inverse function is going to be a reflection over the line y equals x. So every point along our pink line is going to get reflected over the line y equals x. What does that mean? That means if I took a straight line, a perpendicular line from y equals x, and I got this distance, that my new point is going to be the exact same distance on the other side. Where there is no distance between the original graph and y equals x, well, the reflection of that is easy. It's going to go through that point as well. Let's try a couple other points. If I take a perpendicular line straight from there, I'll meet here at a certain distance. I'm going to take that distance and do the exact same distance on the other side. Okay, your graph will be better because you have some lines. Basically, this distance needs to be the same as that distance. This distance needs to be the same as that distance. And that is how I will get my reflection.
What are the numbers though? Like
over the line y equals x.
That doesn't look similar at all.
It's a reflection over the line y equals x.
According to me, those points are...
So where this had a y-intercept of negative 3,
now
This one is going to have an x-intercept of -3.
Good job, Sam.
Okay. What else can we say? Where this has an x-intercept of whatever that is, that value is going to be now here on the y-axis of the inverse function. Basically, you need to know that the straight line across, perpendicular to the line y equals x, equidistant from each, you'll get enough points to sketch your lines. And really, again, all you're doing is switching the x and y coordinates. Okay, you're switching the x and y coordinates.
Oh yeah, literally. Oh,
Okay, the second one is a little bit more challenging. Example 2b tells us that our original function f of x is 2x squared plus 16x plus 29. Now, step 1, I'm going to follow the exact same steps. Step 1, replace f of x with y. Not changing anything else, just calling it y equals instead of f of x equals, because it's easier to swap and deal with y's in here than it is to deal with f of
But it
x's.
means literally the same thing.
It's literally the same thing. Now, this one's a little bit trickier because it's in standard form. I cannot do and undo things in standard form. Okay, for instance, what I would have to do to get this x by itself is different than what I'd have to do to get this x by itself. So what I actually need to do first is rewrite this in a form that has only one x on this side. Now, this is a quadratic equation. You know 3 forms of a quadratic equation. One of them is standard form, which we're in. That doesn't work because it's ax squared plus bx plus c. Factored form does not work because it's x minus r, x minus s.
Vertex.
Vertex form works. Convert to vertex form, which is y equals a x minus h squared plus k. Now, how do I convert to vertex form?
Excellent question.
By completing the square. Isn't that great how math builds on itself and you get to review old concepts
I was
and
really hoping we were past that.
all right,
We'll have
so
to do that on the test.
completing the square. Here we go.
Obviously.
I want to deal with my terms of x, so I'm going to group my terms involving x and I'm going to factor out 2 from them so that my leading coefficient is 1. So I have 2 and what's left is x squared plus 8x. I'm going to close that bracket. Okay, I'm actually going to make it really big so I can save some space. And I have positive 29 out there. He wasn't welcome in the perfect square trinomial party. How do I create a perfect square trinomial? Well, I take half of b and square it. So half of b is 4. I'm going to add 4 squared. If I add it, I've now changed the value, so I actually need to subtract 4 squared as well. Next step, I have my perfect square trinomial here. I can represent it as a binomial squared. It's going to be x plus 4 squared. But before I do that, which I've already done it, but before I do that, I need to kick this guy out of the bracket. His value is 4 squared, negative, so it's negative 16 times 2. He's not going to be in the brackets anymore. He's going to be on the outside. Negative 32, and I still have this positive 29. Wrap it up, one last step. 2 times x plus 4 squared minus 3. Now we're in vertex form. And I can see the vertex is at negative 4, negative 3. I don't need to know that at all. But now my next step is that we are going to solve. We already have y isolated. So what we need to do now is swap our x and our y. Okay, so step 2 here is swap x and y. Swap x and y. Step 2, step 1. So now we have x equals 2 times y plus 4 squared minus 3. Step 3, isolate y. And put a little note here for you. using BEDMAS. Using BEDMAS in reverse. Okay, so when you're solving something, you're using BEDMAS forward, you're thinking about brackets, then exponents, then multiplication, division, then addition, subtraction. When you're finding the inverse, or you're isolating a variable, you're using this in reverse. Let me explain it in another way. You've probably heard me say this before, but here's why. We want to get him by itself. Okay, there he is. But he's stuck to a whole bunch of other stuff. Okay, he's really stuck to this plus 4 because they're inside this group. So they're like really tightly stuck. They're like the inner core. Then when he's with him, they're getting squared. So if I want to undo the plus 4, I have to undo the square first in order to even get into this group. But before I can do that, I have to undo this because this 2 is being multiplied by this whole group.
But before you do that.
But before we do that, we've got this little tail of -3 on the outside. So I'm actually going to strip away from the y what's easiest, what it's least attached to. Is that a good way of explaining this?
Yeah.
Yes.
Okay. So starting from the outside then, what are we going to do first? We're going to add 3 to both sides. So now I have x plus 3 on the left, and on the right I have 2 times y plus 4 squared. So we did addition and subtraction. What's next? Multiplication or division. Okay. I see there's a group being multiplied by 2. What do? Divide both sides by 2. Watch very carefully. The left side is x plus 3, and that whole thing has to get divided by 2. And on the other side, y plus 4 in a group, squared. Now, please pay attention to this. This division line over here has formed a natural group. The numerator is a group, x plus 3, and the whole group is being divided by 2. Okay, it's not the same as x over 2 times 3, or plus 3. It's not the same as x plus 3 halves. It's not the same. It's x plus 3, then divided by 2. Okay, they formed a nice group there. Now, what's my next step? Exponent. How do I undo a square?
Square root.
A square root. Okay, watch. Square rooting both sides. I'm going to do the right side first. The square root of a square is really easy. It's just itself. Well, what is itself in this case? It's the group y plus 4. Y plus 4 squared. If I square root it, I'm going to be left with y plus 4 all by itself. On the left side, I have to take everything that I have, x plus 3 over 2, and square root it. Now, what's interesting about a square root, and we can show it off to the side, but let's say I took the square root of 4. What's the answer? Is that it? Or -2. -2 times -2 is 4. 2 times 2 is 4. So it has 2 square roots. Same thing over here. The answer is plus or minus this. And now we're actually kind of getting close to how you create the quadratic formula. You can notice bits and pieces of this in the quadratic formula. Anyway, the last thing that we need to do is what? To get y by itself. Subtract 4. Please pay attention. It is plus or minus the square root of this whole thing. And I am going to subtract 4 from that whole thing. And that's going to equal my new y.
Wow.
What is the last step?
Graph it. Oh yeah, my bad.
Rename it.
Rename it, rewrite it with inverse notation. And I'm going to put that on the left side, obviously. So we have the inverse function f of x is equal to plus or minus x plus 3 over 2. It's the square root of that
-4.
minus 4.
I wouldn't say it's so simple.
Now, that is, paying attention, that is 2 different functions. Can you see how it's 2 different functions? Because this is You could have positive this minus 4 or negative that minus 4, and they are both needed to create the inverse of a parabola, of a quadratic equation. Okay, we're going to draw that, and it'll make more sense in a second when we do. First step on your graph, you're going to want it, your axis cutting right through the middle.
Ours is like kind of to the right.
That's okay, it is what it is. It's not in a great spot, but that should work. And you're just going to draw your dotted line, y equals x. Okay, y equals x.
Like,
The original parabola is up here in vertex form. It goes through, has a vertex at -4, -3. So go ahead and put a dot at -4, -3. And it has a stretch factor of 2. So where a regular parabola would go through over 1, up 1, paying attention, a regular parabola would go over 1, up 1, over 2, up 4, over 3, up 9, and then same thing this way, 1, 1, 2, 4, 3, 9. We're going to grow twice as fast. So we're actually going to go over 1, up 2. Then we're going to go over 2, up 8. And you're going to have kind of a tall, skinny parabola
there's one up.
that looks like this. I'll give you the, as long as it looks something like this, you're doing fine. Now, when we reflect this over the line y equals x, that means we're taking every point and reflecting it perpendicular to y equals x. Okay? So there's my new vertex. And if I take this point and reflect it, I get this point. And if I take this point, this is going to get a bit confusing for you, so maybe pay attention. But if I take a point over here, consider it away from the line y equals x, I'm going to do the same thing over there. Okay?
You're literally just flipping it.
Yeah, but you're going to end up with something that you maybe weren't expecting. It looks like this
No.
and this.
Tuna.
Okay? And you can kind of see it if I don't mess it up with all sorts of lines. You can kind of see how like this gets flipped to here. This gets flipped to here.
I understand.
Okay? Now,
Oh, I get it.
just you don't really need this, but is this a function? Does this pass the vertical line test?
No.
No. No. The inverse function of a parabola is not a function in and of itself. It is actually built from two functions. Watch. Here's the vertex. What type of function does this look like?
Murder. Murder.
It looks like a root function. And what about this? Well, it's just a vertical reflection of the exact same root function. Look at our equation. Okay? It has two pieces. It has positive square root function and a negative square root function. So the inverse of a quadratic function is actually a combination of two functions. As a whole, it doesn't pass the vertical line test. It's not a function. It's the combination of two functions, which is why this still works. Okay? We did all that algebraically. No problem whatsoever.
I forgot how you graphed that really hard one though.
B says, the second part says graph f of x and its inverse. We did that. Then determine whether or not it is a function. Okay, in example 1, you did a line. So the result was another line, which is a function. In this case, we just had this discussion. Does this blue curve pass the vertical line test? No. So f, the inverse of f of x, is not a function. It is not a function because there are two y values for certain x values. If I put in, for instance, if I put in 2, I might get this value or this value. That means it's not a function. I should get the same thing out every time when I put the same thing in. It's not a function. It's enough for us to say it does not pass the vertical line test. Okay,
Look,
example
Yeah,
3. This goes back to the scenario that we talked about right at the beginning of the lesson. It is the speed of a car with, and then with respect, well, stopping distance with respect to the speed of a car is the original graph. And it's given by this equation. The distance that it takes to stop is equal to 0.006 times the velocity or speed of the car squared. So the speed you would put into this equation and you'd square it and then multiply it by 0.006 and you would get the distance that it takes to stop measured in meters, speed measured in kilometers per hour. So this is the graph. And what's this one called?
The reversed graph.
Inverse.
The inverse. The inverse, okay? The inverse graph. Good.
Speed.
We are first talking about domain and range. So A, you have state the domain and range of function d. That's our original picture. What is the domain? That's all of the values of x that are put into the function. Speed
I am speed.
or velocity. Velocity comes from the set of real numbers. Any restrictions on the velocity here?
No.
Which quadrant are we in?
The right.
The X.
The second
Speed is
one.
always
Zero.
going to be greater than or equal to 0. Very good. Doesn't make sense to talk about negative speed. Speed isn't a directional quantity, although velocity is, so I guess you could have that conversation. But in this scenario, we're going from 0 and positive numbers. Range is the stopping distance, capital D. Comes from the set of real numbers. What's the restriction?
This is so
Zero or
Greater than or equal to 0. Stopping distance is our vertical axis here. It starts at 0 and it can only be more than 0. Can't take you less than 0 meters to stop.
Oh, who knows, right?
Okay? Good. B. So B says determine an equation for the inverse of the function and then state its domain and range. We're going to follow the exact same steps, but we're also going to keep in mind our restrictions. So B says determine the inverse. So we're starting with D equals 0.006 V squared. What do we need to do?
right and Y.
Yeah, we're going to switch D and V, but there's something here that doesn't allow us to do that. 1 second. So in this case, it's saying because the relationship between D and V can't change. So when we did it before, we swapped X and Y, which means the relationship between them changed. This time, the relationship between them can't change. So what it's saying is that what you need to do is simply isolate V as is.
What?
So
we're gonna
don't
do-
swap their places. This time we're just going to isolate. We're going to take V in terms of D, whereas right now we have D in terms of V.
But you
so-
swap them on the graph.
Let's just finish it off and then we'll try to make sense of it.
Okay.
So we're going to divide both sides by 0.06. So that's going to give us D over 0.006 equals V squared. And we're going to take the square root of both sides. So that's going to give us, and I'm going to put V on the left now, V equals the square root of D over 0.006. Do I need to worry about the negative values? No, because the domain and range are both restricted to values greater than or equal to 0. So I don't need to worry about the negative square root of this thing. Okay. Now, our new situation. So the new domain. So this is now, the domain now is the values that can go in are the D values, whereas over here it was the D values coming out and the V values going in. This time when we're doing domain and range, the V values are coming out and the D values are going in. What are the restrictions? A couple ways you can think about that. They're just the opposite of the original.
Not D.
They're just the original flipped. And the other way you could do it is just look at the graph and you're in the same situation. D and V are both greater than or equal to 0. So over here in black, hey, this is what happened if I followed the same steps as before when I switched the variables and then solved for the other variable. We ended up with a D equals situation again. And this relationship is not the same as this relationship. So this is actually just a blanket lie. Okay, so because of this real world situation where there is a set relationship between velocity and distance, we don't swap the variables. That would be to change the relationship. Instead, you're just gonna solve. You're gonna change the independent and dependent variables through algebra. So in the end, D is now the independent variable, and V is the dependent variable. Whereas at the beginning, D was dependent and V was independent.
Kind of a
So this doesn't work.
Why?